Okay, welcome to the next lecture. Today we're going to talk about coal. So the three quasi-final exam questions for today are: what are the principal advantages of coal as a generating resource? What factors are behind the widespread retirement of coal-fired power plants in the U.S.? And what is the projected role of coal-fired generation in the future? So coal is a sedimentary rock, usually occurring in rock strata and layers or veins that are called coal beds or seams. And a picture of a coal bed is shown to the right here. So coal is mostly composed of carbon with hydrogen, sulfur, oxygen, and nitrogen mixed in as well, and traces of bad stuff like mercury, arsenic, and selenium. So let's talk about the advantages of coal as an energy resource first. So the primary advantages are that it's extremely abundant. It's the most abundant fossil fuel on the planet. And in addition to that, the largest deposits are located in regions that are relatively stable politically, such as China, India, and the United States. And so this is in pretty stark contrast to what you'd see if we showed a pie chart of who owns the world's oil reserves. That's sort of a who's who list of countries that are pretty geopolitically unstable. Another advantage of coal is that it's easily stored. Unlike a pipeline technology, you can refine coal, send it to the point where you want to use it, like a coal-fired power plant, and then pretty much just leave it there. So the combination of coal being abundant and easily stored means that coal prices in the United States are pretty low in terms of a dollar per energy content basis, dollars per million BTUs or British thermal units. Pretty low compared to natural gas, and also pretty stable compared to natural gas. This figure shows a comparison of fuel prices of coal and natural gas between 1997 and about 2012. And you can see a lot of volatility in the market for natural gas, and we'll talk about why that exists in another lecture. But for now, I realize that the coal prices are generally pretty low and pretty stable, at least in the United States. And because the price of coal is relatively cheap, what that translates to is a relatively low cost of electricity from power plants that use coal. So we've seen this table before. It just compares different types of generation types according to their variable costs in terms of dollars per megawatt hour. It gives some explanation for why, and then also talks about some of the engineering constraints that are present for these different generation technologies. And so coal, we've talked about before, has a pretty cheap fuel cost, and then as a result, the variable cost of electricity is pretty cheap as well. And I'll also point out here that we can also see the impact of natural gas price volatility, at least compared to coal, on the variable cost of electricity from a natural gas power plant. We see a pretty big range here, at least in an abstract way, represented by these dollar signs. So there are different types of coal, which are referred to as rankings. So coal rankings distinguish between different types of coal according to two different characteristics: their energy content and their carbon content. In both cases, you want higher possible values. So the four different types of coal are anthracite, bituminous, subbituminous, and lignite. Anthracite, I guess you could think of as the most valuable because it has a higher energy content and higher fixed carbon content. And bituminous has higher energy but lower fixed carbon content. Subbituminous has moderate amount of energy content and lower fixed carbon content. And then lignite is sort of the least valuable because it has lower energy content and lower fixed carbon content. So we can sort of visualize the differences between these different types of coal according to these two characteristics. In two dimensions here. On the y-axis, we have the percentage of fixed carbon. And so a higher percentage of fixed carbon means that there's fewer volatile compounds that would be associated with the coal. And the higher energy content on the x-axis, we see the gross calorific value, so energy content. So where you want to be ideally is sort of the top left corner, where you have higher percentage of fixed carbon, fewer volatilities, as well as higher energy content. You can see that anthracite generally takes up that space in the top left corner. And our least valuable type of coal, lignite, is in the bottom right. And just to give you some sort of visual sense for what these different types of coal look like, I've pictured the four types here. This will not be on the final. So a really brief history of the coal industry. And coal has been a source of energy, a fuel source for humans for thousands and thousands of years. Romans were exploiting all major coal fields in Britain by the time they built Hadrian's Wall. Coal's been in use in the Eastern world for thousands and thousands of years. In the industrial era, coal replaced wood because coal has a higher energy content, or higher energy density than wood does, and it was used during the Industrial Revolution to power steam engines. So it helped expand international trade. And then our interest in coal in this respect is in its use as a fuel and electric power plant. So the first electric power plant in the United States was Thomas Edison's Pearl Street Power Station in Lower Manhattan. We've talked about this power plant before. In the context of the history of the electric power industry, this was the first power plant in the United States. Edison's jumbo dynamo used coal as its main fuel source. So modern coal-fired power plants look a little bit like this. So in general, what we're doing is we're converting chemical energy that's embedded in the coal into thermal energy by combusting the coal in a boiler. That thermal energy we're capturing in the form of steam, pressurized steam, which is then passed through open areas and used to spin a turbine. So that thermal energy is transferred to kinetic energy. And then that kinetic energy, we're spinning a coil within a magnetic field and generating electric current, gets eventually translated into electrical energy, which we're then harvesting using transmission lines and sent to where we want that electricity to be consumed. So just sort of zeroing in on the steam cycle here. Remember the Qn here at the very bottom is our source of energy content, the chemical energy content that's embedded in the coal itself. So we're using that in a combustion process. So we're burning the coal. We're doing that specifically to heat up some sort of pressurized fluid, usually water, into steam. And then that steam is allowed to pass through an open area. It expands and cools somewhat. The expansion spins the turbine, which spins the conductor, rotates the conductor within a magnetic field, generating current. And then that steam is then cooled down back into water, and then that water is pumped right through the cycle again. So again, this is just a representation of a simple DC generator. So we have a coil that's rotating within a magnetic field. The source of energy that's rotating the coil itself, in this case, is of course the steam passing through the opening, rotating the turbine. So the use of coal at electric power plants and the expansion of the use of electricity within the United States resulted in massive increases in annual production of coal within the United States. You can see from the beginning of sort of the inception of the electric power industry in the 1880s, there's this rapid increase in annual production of coal. The role of the electric power industry and the role of having cheap electricity and the importance of that to the economic development of the United States was tied directly to the abundance of and use of cheap coal in the United States. So today, coal power plants are generally operated as baseload, which means they provide fairly steady generation throughout the day, week, and year. But they're more flexible operationally than nuclear power plants, so they commonly ramp up and down as needed. And they can shut down completely during low demand periods. Traditionally, their placement within the system supply curve has been sort of above nuclear but below natural gas. That's changing a little bit because of the price of natural gas being so low in recent years. Um, but typically they would be in the middle of the system supply curve, providing electricity as a baseload resource and occasionally as sort of a shoulder resource, helping to ramp up a little bit during higher demand periods, but not enough to fully meet peak loads. And so that's what this shows here. We've seen this figure before. This is sort of a typical least cost economic dispatch schedule for a system of power plants. We're using nuclear as base load, wind and solar whenever the wind is blowing, the sun is shining. Coal here is providing fairly stable supply of electricity. It's providing more during high demand periods and a little bit less during lower demand periods. And then natural gas and hydropower are peaking resources.